often told that the Second World War was won by the grit of the infantry and the courage of the greatest generation. But in the summer of 1944, courage wasn't enough. London was being systematically dismantled by an enemy that didn't have a heart, a pilot, or a soul: the V-1 flying bomb. Our best gunners were firing thousands of shells into the blue, hitting nothing but air. It was a crisis of human limitation, until a group of slide rule engineers in a Massachusetts lab handed the military a secret trailer that could see the invisible. Today, we're looking at the SCR-584, the machine that took the war out of human hands and birthed the automated world we live in today.
You know, there's a specific kind of silence that older folks like us remember, the kind that exists right before a storm breaks. But in the summer of 1944, for the people of London, that silence was replaced by the sound that would haunt a generation: the low, mechanical rattle of a pulse jet engine. They called it the Doodlebug, the V-1 flying bomb. It was history's first true cruise missile, a pilotless, mindless machine that didn't care about courage or chivalry. It just flew until its timer ran out, and then it fell. For the men tasked with defending the White Cliffs of Dover, the problem wasn't just the speed of these things, it was the invisibility of the threat. Traditional anti-aircraft fire was a game of manual estimation, young men squinting through optical sights, trying to hit a speeding hummingbird with a garden hose. It was like trying to hit a speeding hummingbird with a garden hose. We had the Great Wall of anti-aircraft batteries, hundreds of guns lined up along the coast, but against the V-1, that wall was made of glass. The reality was staggering. In those early weeks of the V-1 campaign, our Great Wall was failing. It took an average of thousands of shells just to bring down a single flying bomb. The British 3.7-inch guns and the American 90mm batteries were powerful, but they were blind in the way that mattered most. They relied on the SCR-584 Radar, a primitive system that was easily jammed and suffered from ground clutter. It couldn't see the V-1s because they flew too low, between 2,000 and 3,000 feet, blending into the echoes of the Earth itself. But then the tide turned through a marriage of two impossible American technologies, the SCR-584 Radar and the M9 gun director. The SCR-584 wasn't just a better eye, it was a robotic one. Developed at the MIT Radiation Laboratory, it used a breakthrough called conical scanning. Instead of a wide, blurry beam, it projected a tight 4-degree pencil beam of microwave energy that rotated like a spinning top. This allowed the radar to lock on to a target with a precision of 0.06 degrees. Therefore, for the first time in history, the human element, the shaking hands and the guesswork of leading a target, was removed from the equation. The radar saw the V-1, and the M9 analog computer calculated the kill. The results were nothing short of a massacre for the Luftwaffe's vengeance weapons. Once the SCR-584 was paired with the newly arrived Proximity Fuze, a tiny radio station inside a shell that exploded when it got near the target, the Great Wall became a wall of literal light and steel. By August 1944, the kill rate for guns on the coast jumped from a pathetic few percent to over 74%. On one miraculous day, the system knocked down 82% of everything the Germans launched. We went from spending thousands of shells per kill to just 100. It wasn't just a tactical win, it was the birth of automated warfare. The invisible invader had met a machine that could see the unseeable, and in doing so, it saved London from a second Blitz that could have leveled the city.
If you were to look at the English coastline in 1940, you'd see these massive skeletal steel towers, some over 350 feet tall, looming over the cliffs like something out of a science fiction novel. This was the chain home system. To the men of that era, it was a miracle. It was the radar that won the Battle of Britain. But as much as we respect those old giants, they had a fatal flaw that almost cost the Allies the war. You see, these radars worked on long wavelengths, about the length of a family sedan. Because the waves were so big, the equipment had to be even bigger. They were blind giants because while they could see a fleet of bombers coming from 100 miles away, they couldn't see anything low to the ground. They were like a man who can see a mountain on the horizon but can't see the tripwire at his feet. If the Germans flew low, or if they sent a single small target like a V-1, the chain home towers were essentially useless. We needed a way to shrink the waves down to the size of a teacup to microwaves. But in 1940, no one on Earth knew how to generate that kind of power in such a small package. Everything changed on a cold February morning at the University of Birmingham. Two researchers, John Randall and Harry Boot, were staring at a device that looked less like a weapon and more like a heavy copper hockey puck with holes drilled into it. This was the first cavity magneton. History suggests that many breakthroughs come from simplifying the complex. Randall and Boot stopped trying to make bigger vacuum tubes and instead looked at the physics of a whistle. You know how when you blow across the top of a soda bottle, it makes a specific note? They applied that same logic to electrons. Inside that copper block, they carved out 6 circular cavities. When they pushed electricity through it, the electrons would whistle past those holes, vibrating at a frequency so high it produced 10-centimeter microwaves. The power jump was staggering. Before this, the best microwave generators could only produce about 10 watts, barely enough to light a dim bulb. The cavity magneton instantly pumped out 400 watts, and within weeks they had it up to kilowatts. When the British eventually brought a prototype to the U.S. in the famous Tizard mission, American scientists were stunned. One historian called it the most valuable cargo ever brought to our shores. The invention of this whistling copper block did more than just improve radar. It made the blind giants obsolete. But more importantly, it allowed radar to be miniaturized. For the first time, you could fit a radar set into the nose of a night fighter or onto the back of a mobile truck. This was the birth of the S-band radar, the very eye that would eventually power the SCR-584. But there was a catch. Having a powerful eye is one thing. Having a hand that can move the gun fast enough to keep up with what the eye sees is quite another. We had solved the problem of seeing the invader, but we were about to realize that the human brain was now the slowest part of the defense. If you ever spent time under the hood of an old '57 Chevy, you know that there's a limit to how fast a human can react to a mechanical problem. Now, imagine that problem is a V-1 flying bomb screaming toward London at 400 miles per hour. In the early 1940s, the way we fought back was through a chaotic, sweating mess of human error called manual tracking. Think about the physics of it. To hit a moving target with a 90mm anti-aircraft gun, you can't just aim at the plane. You have to aim where the plane will be when the shell arrives, a concept called lead. In 1940, this was done by 3 or 4 young men sitting on the gun carriage, frantically cranking wheels. One man tracked the elevation, another tracked the bearing, and a third tried to guess the range based on what he saw through a telescope. It was a symphony of guesswork. If one man's hand slipped, or if the smoke from the last blast stung his eyes for just a second, the shell would miss by hundreds of yards. Therefore, despite having the best guns in the world, our defense was a sieve. We were using 19th century reflexes to fight a 20th century machine. The British and American high commands realized that if they didn't take the Schumann out of the loop, the war would be lost to the sheer volume of German production. This realization led to what history now calls the impossible directive given to the MIT Radiation Laboratory, or the Rad Lab. The directive was simple but terrifying. Create a system where the radar doesn't just find the target, but locks onto it and steers the gun automatically. In 1940, this sounded like witchcraft, but the Rad Lab, filled with the brightest minds from industry and academia, began working on a concept called automatic angle tracking. They realized they needed two things that didn't exist yet: a way for the radar to know it was off-center, and a way for that information to move a 5-ton gun barrel with the precision of a watchmaker. This led to the development of the conical scan. Instead of the radar beam pointing straight ahead, they made the beam spin in a tiny circle, like a flashlight being wobbled by a nervous hand. If the target was perfectly centered, the echo coming back was steady, but if the target moved slightly to the left, the echo would get stronger when the beam swung left and weaker when the beam swung right.
The radar finally had a brain. It could sense its own error. But the impossible directive went one step further. They paired this radar with the Bell Labs M9 Director. This was a massive analog computer, not a digital one like the phone in your pocket, but a machine made of gears, cams, and vacuum tubes. It took the electrical signals from the SCR-584 and instantly solved the calculus of the lead angle. The payoff was a mechanical revolution. When they finally hooked the SCR-584 to the M9 and then to the gun's power drives, the gunners actually stepped back. They watched in awe as the massive 90mm barrels moved on their own, twitching and pivoting with eerie robotic smoothness, following a target they couldn't even see with the naked eye. The chaos of manual aiming died that day in the Rad Lab. We had replaced the shaking hand of a 19-year-old with the cold, calculating precision of an electrical circuit. But as brilliant as this eye and brain were, they were still firing a dumb bullet. Even if you aim perfectly, if the fuse doesn't blow at the exact millisecond it passes the target, you've still missed. The machine was perfect, but the ammunition was still stuck in the past. If you grew up in the era of mechanical watches and vacuum tube radios, you understand that there is a certain soul in a piece of machinery that works perfectly. By 1943, the SCR-584 was that machine. It was the Rolls-Royce of radar, a masterpiece of American engineering that felt less like a tool of war and more like a scientific instrument. It was housed in a massive four-wheeled trailer that looked like a common bread van, but inside it was packed with over 400 vacuum tubes and the most sophisticated microwave circuitry on the planet. However, even with this masterpiece, we were facing a heartbreaking mathematical reality. You could have the most precise radar in the world, a system that could see a baseball-sized target from miles away, and you could have an analog computer that predicted its flight path to the inch. But all of that precision ended the moment the shell left the muzzle of the gun. Why? Because we were still relying on the time fuse. Think of a time fuse like an old-fashioned kitchen timer screwed onto the nose of an explosive shell. Before the gun fired, a soldier had to manually set that timer based on the radar's calculation. If the radar said the target was 4,000 yards away, you set the fuse for, say, 10.2 seconds. But if the timer was off by even a tenth of a second, or if the V-1 flying bomb changed its altitude by just 50 feet, the shell would explode harmlessly in the empty sky. We were throwing million-dollar technology at a problem, only to be betrayed by a mechanical timer that cost $5. Therefore, we were still missing the invisible invader far more often than we were hitting it.
The SCR-584 was, by all accounts, a technical marvel that pushed the boundaries of what was physically possible. It utilized a 3,000 megahertz signal, which allowed it to cut through the ground clutter that had blinded previous radars. While the older SCR-268 radar was like trying to see through a foggy window, the 584 was like a laser beam. It was so accurate that it didn't just tell you there was a target over there. It could tell you the target's exact coordinates within 0.06 degrees of azimuth. The secret to this precision was the automatic tracking feature. Once the operator found a target on his scope and locked the system, the radar dish would begin to twitch and turn, following the V-1 across the sky with a smooth, eerie persistence. It used servo mechanisms, heavy-duty electric motors that translated the tiny electrical pulses from the radar into the massive physical force needed to move the dish. But here is where the frustration set in for the men on the ground. During testing at the Anti-Aircraft Artillery Board, they found that the SCR-584 and the M9 Director were so accurate that they were consistently placing shells within yards of the target. In the world of artillery, that's a sniper's grade shot. But against a V-1, a miss by 5 yards might as well be a miss by 5 miles. The shell would whistle past the flying bomb, explode behind it, and the Doodlebug would just keep rattling along toward London. The fuse problem was the final bottleneck. We had perfected the eye, the SCR-584, and the brain, the M9, but the fist was still clumsy. We were using mechanical clockwork fuses that were susceptible to temperature, humidity, and the massive G-forces of being shot out of a cannon. History suggests that during this period, even with the world's best radar, it still took an average of 2,500 shells to bring down a single V-1. The engineers realized that to kill a machine as fast and small as the V-1, they couldn't rely on a timer. They needed the shell to know when it was close to the target. They needed the shell to have its own eye. This led to the next desperate leap in technology, one that was so secret the soldiers using it were told they would be court-martialed if they even talked about the shape of the fuse. In the world of engineering, we often talk about the missing link, that one final piece of the puzzle that turns a noble failure into a world-changing success. By 1944, the Allies had the best radar in the SCR-584 and the best computer in the M9. They were 2/3 of the way to a miracle. But as we discussed, the time fuse was the weak link. It required a human to guess the future. If you've ever tried to lead a fast-moving bird with a shotgun, you know the frustration. Now imagine that bird is a ton of high explosives moving at 400 miles per hour, and your shot has to be timed by a mechanical clock to explode within a 50-foot window. The scientists knew that if they could just make the shell intelligent, if they could make it explode only when it felt the presence of the enemy, the V-1 threat would vanish. But the challenge was almost laughable. They needed to fit a radio transmitter, a receiver, and an antenna into the nose of a shell, while ensuring the whole thing could survive being spun at 25,000 RPM and subjected to 20,000 Gs of force upon firing. It was like building a glass radio that you could shoot out of a tank and expect it to work. This led to the birth of the VT fuse, variable time, better known as the Proximity Fuze. While the SCR-584 was the eye and the M9 was the brain, the Proximity Fuze became the nervous system of the shell. It was a masterpiece of ruggedized miniaturization. Inside the nose of each 90mm shell sat 5 tiny vacuum tubes protected by a special potting compound that acted like a shock absorber. The marriage of these technologies was a stroke of strategic genius. Therefore, the workflow of death for a V-1 looked like this. The SCR-584 would pick up the Doodlebug over the English Channel. It would lock on and automatically feed the coordinates to the M9 director. The M9 would then calculate the lead and electronically aim the 90mm guns. But here was the game changer. The loaders no longer had to set a timer. They just shoved in a shell equipped with a Proximity Fuze. When the gun fired, the shell would emit its own tiny radio signal. As it closed in on the V-1, those radio waves would bounce off the metal skin of the German bomb and return to the shell. When the signal reached a certain strength, indicating the shell was within about 70 feet of the target, the circuit closed. Boom! The impact of this deadly duo was immediate and devastating. In the first weeks of the V-1 campaign, it took roughly 2,500 rounds to down one bomb. Once the SCR-584 was married to the Proximity Fuze, that number plummeted to nearly 100 rounds per kill. We weren't just shooting at them anymore. We were creating a curtain of steel that the V-1s simply could not fly through. However, this marriage was so potent that the Allies were terrified the Germans would find a dud shell, reverse engineer the fuse, and use it against our own bomber streams. Therefore, the use of the Proximity Fuze was strictly forbidden over land for months. It was only allowed to be fired over the ocean, where a miss would result in the shell sinking to the bottom of the sea. But as the V-1s began to rain down on London with increasing frequency, the impossible choice had to be made: keep the secret or save the city. History suggests that the decision to unleash the duo was the single most important turning point in the defense of Britain. The marriage was complete, and the results would soon leave the German High Command wondering how their invincible vengeance weapon was being swatted out of the sky like flies. In the high-stakes game of global conflict, there comes a moment where you have to move all your chips to the center of the table. For the British and American commanders in July 1944, that moment was Operation Diver. The V-1 Doodlebugs were terrorizing London, and the scattered inland gun batteries were struggling. The fragments from exploding bombs and falling shells were hitting civilians, and the heavy smoke of the city made tracking nearly impossible. Therefore, a radical, almost desperate plan was hatched. Pick up the entire anti-aircraft defense of London, hundreds of massive guns, thousands of men, and tons of equipment, and move them to the narrow strip of coastline along the English Channel. The goal was to create a literal dead zone. If a V-1 crossed the water, it had to run a gauntlet of automated fire before it ever reached a farmhouse or a factory. But this move was a massive gamble. By placing the SCR-584 units on the coast, they were exposing their most top-secret technology to the elements and potential German recovery. More importantly, it was the first time in history that humans were being asked to step back and let a machine decide who lived and who died. For the veterans of the Great War who believed in the man behind the sights, this shift to automation felt like losing the very soul of the soldier. The result of this relocation was nothing short of a mechanical massacre. By the time the guns were settled into the mud of the coast, the deadly duo of the SCR-584 and the Proximity Fuze was unleashed. Operation Diver transformed the coastline into a laboratory of automated destruction. The SCR-584 units were lined up like silent sentinels, their parabolic dishes scanning the horizon for the telltale signal of a pulse jet. Because they were now firing over the ocean, the radar clutter was gone. The eye was perfectly clear. When a V-1 was detected, the information didn't go to a human who had to think. It went to the M9 director, which commanded the guns. The statistics from this period are the kind that make historians do a double-take. In one single week in August, the diver guns destroyed 82% of all V-1s that entered their zone. On August 28th, the performance reached a peak of terrifying efficiency. Of the 94 V-1s that approached the coast, the automated batteries swatted 82 of them out of the sky. Only 4 reached London. History suggests that without this 15-mile strip of automated defense, London might have become a graveyard. However, as the kill counts rose, a strange and quiet unease began to settle over the men. They were no longer gunners in the traditional sense, they were machine tenders. They spent their days hauling heavy shells and cleaning grease, while the actual warfare, the tracking, the aiming, and the timing, was being done by a series of vacuum tubes and spinning gears inside a trailer. This was the moral toll of automation. For the 65-plus generation of that time, there was a sense of pride in marksmanship. But with the SCR-584, the glory belonged to the engineer in Massachusetts, not the soldier in the mud. There were reports of gunners feeling a strange disconnect, a numbness to the destruction they were causing. They weren't fighting a pilot, they were a machine killing a machine. Operation Diver wasn't just a military victory, it was a psychological threshold. We had proven that a machine could defend us better than we could defend ourselves. We had traded the heroism of the individual for the efficiency of the algorithm. As the last V-1s were knocked into the sea, the world was left with a chilling realization. The era of the primitive was over, and the era of the push button had begun. The Great Wall of Light had held, but the role of the soldier had been changed forever. When the smoke finally cleared from the cliffs of Dover and the last of the pulse jet echoes faded into history, the world woke up to a reality it wasn't quite prepared for. Often we look back at the Second World War as a triumph of grit, of men in trenches and pilots in dogfights. But those of us who have lived through the rapid acceleration of the 20th century know that the real V-Day occurred in the quiet humming of a radar trailer. The SCR-584 didn't just stop a bomb, it stopped an entire way of thinking. For thousands of years, warfare was a contest of human senses. Who could see the farthest? Who could aim the truest? Who could react the fastest? But the primitive era of the human eye ended in 1944. We had crossed a bridge, and there was no going back. The question that remained for the post-war world wasn't just how we would use this machine's eye, but what it would do to us. If a machine could outthink and out-aim a man in 1944, what would it be capable of when we were no longer around to watch the scopes?
The legacy of the SCR-584 and the cavity magnetron is woven into the very fabric of our modern lives, often in ways we take for granted. Therefore, when you stand in your kitchen and heat up a cup of coffee, you are using the direct descendant of the V-1 killer. The microwave oven exists only because an engineer named Percy Spencer, working for Raytheon on magnetron tubes, noticed a candy bar in his pocket had melted. The same waves that scanned the English Channel for Nazi bombs are now used to pop popcorn in our suburban kitchens. It is perhaps the most peaceful legacy a weapon of war has ever left behind. But the technological lineage goes much deeper than kitchen appliances. The SCR-584 was the great-grandfather of the Global Positioning System, GPS, and modern air traffic control. The principles of conical scanning and automated tracking paved the way for the systems that keep thousands of commercial airliners from colliding every single day. We traded the Great Wall of Light for a global net of safety. History suggests that the SCR-584 also gave birth to the digital age. The M9 gun director was one of the most successful applications of feedback loops, the idea that a machine can monitor its own performance and correct its errors in real time. This is the fundamental logic behind everything from the cruise control in your car to the algorithms that run the internet.
We moved from a world of action and reaction to a world of data and optimization. However, we must also look at the darker side of this heritage. The success of the deadly duo gave the military-industrial complex a blueprint for the future, the smart weapon. The V-1 was a primitive, dumb cruise missile, but the system that defeated it was the ancestor of the Patriot missile and the Iron Dome. We entered an era where the human element is increasingly sidelined. Today, we have drones that can identify targets from miles away and autonomous systems that make decisions in nanoseconds. The moral toll we felt on the coast of England has become a permanent feature of modern existence. In the end, the story of the SCR-584 is a story of American ingenuity at its absolute peak. It was a moment when the Rad Lab kids and the Bell Labs engineers outthought the vengeance of a dictator. But as we look back from the vantage point of the 21st century, we realize that the machine's eye never closed, it only got sharper. We live in the world the SCR-584 built, a world of incredible precision, undeniable safety, and a lingering, quiet question about where the machine ends and the human begins. The primitive era is gone, and in its place we have the Great Wall of the digital age, unseen, ever watchful, and born from a copper hockey puck and a desperate summer in 1944. History is more than just dates on a calendar. It's a collection of stories and technical marvels that shaped the world we grew up in. If you remember the days of vacuum tubes and mechanical precision, or if you simply believe that these stories of ingenuity deserve to be preserved for the next generation, then I'd be honored to have you join our community. Subscribe and click the notification bell to ensure you don't miss our next deep dive into the machines that defined an era. And before you go, I'd love to hear from you in the comments. Do you remember the first time you saw a piece of technology that felt like the future? Let's keep the conversation and the history alive together.